Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. In the last few lectures, we discussed about the multivariable optimization problem with equality constraints. In that process, we saw various methods to solve such problems. In the solution process, we discussed how we can identify the dependent variables and replace them with the independent variable and convert the problem into unconstrained multivariable optimization problem and solve it. The few methods which we discussed are direct substitution method, constraint variation method, and Lagrange multiplier method. In the direct substitution method and constraint variation method, we found out the process by which we can satisfy the necessary condition and identify the points where we can find the optimum values. Then we move to the sufficiency conditions to confirm whether the obtained solution is the maximum, the minimum, or neither of them. In the whole process, we found out that the method could be quite cumbersome or quite involving the moment the number of constraints increases and the constraints are also non-linear. So we also looked into an alternative method, or we looked into a method which is Lagrange multiplier. In this method, we use the determinant equation to identify whether a particular solution is the maximum, minimum, or neither of them. So with this, when we looked into the problem, we also understood that in various practical engineering problems, the equality constraints are not always feasible, or rather it is not very common. On the other hand, multivariable optimization problem with inequality constraints are very common in the practical engineering problems. So today we are going to discuss about the multivariable optimization problem with inequality constraints. So let's first see how we can represent the multivariable optimization problem with inequality constraint. Here is the generic form of multivariable optimization problem with inequality constraints. So the first part here, it represents the objective function which we need to minimize or maximize, and in this capital X represents an array of n number of variables, and then we have the constraints. These are the inequality constraints, which also represents the number of constraints between 1 and m. So this is what a multivariable optimization problem looks like with inequality constraints. Now these inequality constraints can be easily transformed into equality constraint by adding the slack variables. In this case, we are adding the slack variable of yj square with the inequality constraint gj to make it an equality constraint. Here we have added the yj square to ensure that it can take both negative as well as positive without compromising the effect of the slack variable in the process. So once we add this, my multivariable optimization problem with inequality constraints is going to transform into multivariable optimization problem with equality constraint, and this problem is going to be like this, where this is my objective function and my constraints, in this case the equality constraints, are going to be of this form, where we have added the yj square, and since yj square is a variable, it is considered in the constraint function as capital Y. And again, the yj is representing m number of variables, or it represents m dimensional array as shown here. Now once we transform it into an equality constraint, the multivariable optimization problem can be solved or represented in the form of Lagrange multiplier. So the common Lagrange multiplier function now is going to look like L, X, Y and lambda. Y is to take care of the inequality constraint, converting it into an equality constraint, or considering it, or where the y represents the slack variable, and the function is going to be fx and the summation of each of the constraint which we have, and it looks very much similar to our equality constraint multivariable optimization problem. Now when we do the partial derivative of the Lagrange function to obtain the necessary conditions, then we can see that we can actually do the partial derivative with respect to the variables, with respect to the Lagrange multiplier, and with respect to the slack variables. So if we are doing the partial derivative with respect to the variables, then we obtain this equation, which is going to be equal to 0 as part of the necessary condition, and we are going to obtain n number of such equations. Now when we do the partial derivative with respect to the Lagrange multiplier lambda, we are going to obtain m number of such equation, and those are going to be equal to 0. And here is the equality constraint which we had formulated from the inequality constraint. So satisfying this means we have satisfied the equality constraint along with the slack variable. The third set of equations, when we do the partial derivative of the Lagrange function with respect to the slack variable, we are going to obtain an equation of this form, which is going to be equal to 0, and these are going to be of m in numbers. So in total we are going to get n plus 2m number of equations to solve as many number of variables. Now in this necessary condition, which we had easily represented the Lagrange function as this, and in the necessary condition the partial derivatives which looks like this is equal to 0, this is equal to 0, and this is equal to 0. In this we said that these equations would yield n plus 2m number of equations for equal number of unknowns. So we have n number of variables, m number of Lagrange constants, and m number of slack variables. So together we are going to have n plus 2m number of unknowns. So solving this n plus 2m equations for n plus 2m number of variables, we can easily obtain the optimum solution vector for x Lagrange constants or multipliers and the y, that is the slack variable. Now one thing we can notice in the last equation of the necessary condition, so if this is my equation number 1 for the necessary condition, this is my equation number 2 for the necessary condition, and this is my equation number 3. So in this last equation in the necessary condition, we see the term 2 times lambda j times yj is equal to 0. It indicates either my lambda j is equal to 0 or yj is equal to 0. And if we say that lambda j is equal to 0, then the corresponding constraint will become inactive at that point. If we say that yj is equal to 0, the corresponding constraint gj is going to be active and the optimum point is going to lie on that constraint, and for that reason, for the active constraint, gj is going to be equal to 0. It is quite a good finding because with the help of this we can actually reduce the number of equations which we need to solve. So let's see how we can reduce the number of equation. Now, as we said that we have the set of active constraints and the set of inactive constraints. We can indicate the active constraints as J1 and the inactive constraints as J2. Now, as per the necessary condition, when we do the partial derivative with respect to the variables, we are going to obtain n number of equations which we need to equate to 0, and in this, of course, it is going to represent the active constraints, because in other cases my lambda value is going to be 0, so those are not going to be present in these equations. Now, when we looked into the second necessary condition, then we can easily say for the active constraints my y values are 0, so we can clearly write the second necessary condition as gj is equal to 0, because y has already become 0 as these were the active constraints. In the same set of necessary condition, if we again look for the inactive constraints, then we have to say that gj needs to be added with the slack variable, then it is going to be 0. So this is going to be the active constraints and these are going to be the inactive constraints. So together these are the total number of constraints. It indicates that the total number of constraints is m. So the three component here, I would say I, this is I would say 2i's or 2, and this is 3. So these three component we can, if we try to solve, then we have n plus m number of equations for equal number of variables, and if we solve we can easily obtain our solutions for the optimum x star, lambda star and y star. So if we understand the active constraint and the inactive constraint and we identify them appropriately, then instead of solving n plus 2m number of equations for equal number of unknowns, we are solving n plus m number of equations for equal number of unknowns. So it is going to reduce the computational burden. Now let us look into how we can solve and what it means. And in this case, our primary solution is this number 1 equation, where we are doing the partial derivative of the Lagrange function with respect to the variables one by one. So in this, if we identify that the first p active constraints are represented in such a way that that first equation is satisfied, then we can easily write the equation in this form. So these are only the active constraints. The inactive constraints are not here, and this represent n number of equations. So in a generic form, we can say the gradient of f, the negative gradient of f rather, is equal to the Lagrange multiplier with the gradient of the first active constraint, the second Lagrange multiplier with the second active constraint, and so forth, and total p number of active constraints. And this negative gradient of objective function is represented by the linear combinations of the active constraint gradient. Now in this we'll see that for a minimization problem, this active lambda are going to be positive, or rather we say that the lambdas corresponding to the active constraints are going to be positive. Similarly, for the maximization problem, we'll see that the lambda j corresponding to the active constraints are going to be negative. For this, we need to have the understanding of lambda values in this equation. So let us look into that aspect. Now in that particular equation, where we are representing the gradients of the objective function and the constraint, we want to identify a search direction where a small step along that search direction is going to remain within the feasible region. In this case, let us represent that search direction by S. So if we try to pre-multiply that search direction with the gradient, which is represented by this, is going to be represented by this equation. Now, as we said that the search direction is a feasible direction where we can take a small step along that direction without leaving the feasible search space, which means that search direction which we got when we pre-multiply with the gradient of the constraints, it must satisfy the relation of the constraint which are actually less than 0, as those constraints were considered at the beginning. So all the constraints, or particularly the active constraints, were less than 0, and that is what we are saying, our search direction when it's pre-multiplied with the gradient of the active constraints, it is going to be less than 0. Now if all these are going to be less than 0, which means all are negative, then to keep all of them negative, we must ensure that all the lambdas are going to be positive. Then this expression, the right hand side of the equation, we can say for sure is going to be negative. If the lambda have all negative value, then this is going to be positive. So first let us examine what is going to happen if all the lambdas are going to be positive. So if they are positive, this right hand side, as I indicated, it is going to be negative, and if it is negative, means my sign of the left hand side is matching, which means this has to be positive. So we are saying that the objective function value is only going to increase in the S direction. So we have chosen the S direction, and in that direction my objective function value is going to increase because this part is supposed to be positive. So in other words, if we are standing at a point, or if you are at a point, from there we are trying to find a direction in which all the constraints are satisfied, rather the active constraints are satisfied, and the Lagrange multipliers are found to be positive, then we are saying in that direction my function value is going to be increasing, which means that we are actually at the minimum point. Any direction, if we move from that, our function value is increasing. If we want to minimize a function, we should not move from that particular location, which means for a minimization problem we have already reached the minimum point, and if we find that all the lambda values are positive for the active constraints, then we can surely say that we have reached the minimum function value, or we have reached a point where the function value is minimum. On the contrary, as I said, if my lambda values of the active constraints are negative, then my right hand side of the equation is going to be positive, and in order to make the sign equal, my right hand side of this component should be negative, because it has already a negative sign outside. These two together is going to make it a positive. So in that situation, it indicates if we try to move along that feasible direction, my function value is going to decrease.